In today's lesson, we're going to be talking about the definition of the integral. Now, in the last lesson, we talked about the very basics of integrals, how to solve indefinite integrals, what they look like, some of the notation, some of the strategies to solve, the very basics. But the one thing that was definitely not explained is what is actually happening when we take an integral. We do know that whenever we take the integral of a function f prime of x, say this is the derivative of some function, it outputs f of x, the original function. But other than that, we don't really know much about integrals or what's happening when we do them. So that's what this video is going to be about. But first, we're going to talk about something that may seem unrelated at first, but will make more sense later on. So let's talk about summation of series. The summation symbol looks something like this. The basic notation is I equals 1 to n of ai, and a is a function with index I, and this is equal to a1 plus a2 plus ... plus an. This is the summation of a series. We go from index I equals 1, or at least in this case it's 1. It could be 0, it could be some other number, and we go to arbitrary number n. This could be pretty much any number. We start at a of 1, since we started at index equals 1. Then we go to the next index and the next one until we reach our number n. This is the most basic version of a summation series. Pretty much any function can be turned into a summation series, and I promise this will make more sense in just a few minutes. Let's do a couple of very simple examples of summation series. First of all, we have the summation of I equals 1 to 6 of I, the function I. This is equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6, and that is all equal to 21. This is the summation of this series I. We started at index of I equals 1 and then went up 1 every time until we reached 6. So 1, 2, 3, 4, 5, 6. Since we're going to 6, this is where we stop, and this summation is all equal to 21. Now let's do one more slightly more complex example. We have the summation of I equals 1 to n, so no specified ending, of 1 over n times k squared plus 1. This may look a little bit complex, but it's not too bad. Let's walk through it here. So our first index is 1 over n times 1 squared plus 1, plus our second index of 1 over n times 2 squared plus 1, and then ... And then eventually we end up at 1 over n times n squared plus 1. Whatever our n number is, but since we haven't specified an n here, we just go to n, and this would be the last index in our summation series, or I should say the last element or last property in our summation series. K represents whatever index we're on, so obviously k of I equals 1 is just 1, and then 2, and then 3, and then 2, whatever n is. This n could be 3, this n could be 7, this n could be 130, this n could be infinity. Point is, we just add a bunch of stuff together using a summation series. One more thing about summation series before we go too much further, I'm going to give you some basic examples of summation series that could come up later in this video or just later in your math classes. There's going to be 4 of these, so the first one is the summation of I equals 1 to n of c, c being some constant. So this would be equal to c1 plus c2 plus ... plus cn. And this is just multiplication. If our n is equal to 3, we go to c1 plus c2 plus c3, which is the same thing as multiplying c by 3. So this is just the summation series of multiplication. Our second formula for summation series is the summation of I equals 1 to n of I. We just did this one a second ago, but our n was 6, not some arbitrary function. The formula that can solve this summation is n times n plus 1, all divided by 2. As an example, since we just did 6, we know that 1 plus 2 plus 3 plus 4 plus 5 plus 6 is 21. But since n is 6 in this case, we can just plug in 6 to this formula. We have 6 times 6 plus 1, which is 7, so 6 times 7 is 42, all divided by 2 is 21. So this equation holds. We got 2 more. Let's do our third summation series shortcut. This is the summation of I equals 1 to n of I squared. This one's a little bit more complex, but still not too bad. This summation is equal to n times n plus 1 times 2n plus 1, all divided by 6. So if we kept plugging our index and squaring it and adding it up over and over again until we get to n, we could just plug an n to this formula and we would get the same answer. And then the fourth and final one is just this. The summation as I equals 1 to n of I cubed. This summation is equal to n squared times n plus 1 squared all divided by 4. If we were to keep cubing every single index until we reach n, we could just plug an n to this formula and we figured out what the summation would equal. One or more of these may come up later in the video, but what does all this have to do with integrals? That's a great question. Let's talk about particles and do some examples so that way you understand why we're doing all of this. And don't worry, this is not a physics lesson. I'm also bad at physics, don't worry. We are just going to use the particle as an example. It could also be a car, it could be a person, it could be whatever object you want it to be. We're just going to use a particle for this example. So let's say I had this green particle here. This green particle travels at 5 feet per second. If it travels for 3 seconds, how far did it go? Well, that's pretty easy to do. If we know that it travels 5 feet every 1 second, we just know that multiplying 5 times 3 seconds will give us how far it went. This, of course, is equal to 5 times 3, which is just 15 feet. Pretty easy, right? Well, let's add one wrinkle to it. Let's say now we have this blue particle here. This blue particle travels 5 feet per second for 1 second, but then it changes to travel 3 feet per second, or 3 feet per second, but for 2 seconds. How far does it go this time? Well, it's still not very difficult. We just have to add an extra step. It's not as easy as 5 times 3. In this one, we have to multiply 5 feet per second times 1 second, and then add 3 feet per second times 2 seconds. It went 5 feet per second for 1 second, and then 3 feet per second for 2 seconds. So 5 times 1 plus 3 times 2. This is equal to 5 plus 6, which is just 11 feet. But now we're going to throw in a real curveball. This one's going to be a lot tougher. Let's say we have the red particle. He's the real devious one here. He's traveling with a velocity with respect to time equal to t squared plus 1. How far did this particle travel in 3 seconds? So how do we solve this one? We could break it up into parts, and we may as well try that now. Let's say that we split this up into 3 intervals. Let's split this up into the interval of the 0 seconds to 1 second, unionized with 1 second to 2 seconds, and then unionize one more time of 2 to 3 seconds. We have split this velocity graph into 3 chunks. We know how far it can go within these 3 chunks. Using left endpoints, we need to find its velocity with respect to time at 0, and then at 1, and then at 2, and if we add those together, we should get the right answer on how far this particle traveled, right? Well, let's do the math here. At v of 0, it goes 0 squared plus 1, which is equal to 1. V of 1 is equal to 1 squared plus 1, which is equal to 2. And V of 2 is equal to 2 squared plus 1, which is equal to 5. Adding all these together, we get 1 plus 2 is 3 plus 5 is 8 feet. But I'll tell you now, that's not the right answer. First of all, the really obvious part, we're missing the entire 2 to 3rd second interval because we're only using the left endpoints on all of these. If we were to use the right endpoint, we'd be missing the 0 at the beginning. So we're missing something here. What's going on here? What do we need to do to make this work? Well, one solution would be to split it into even more pieces, but if we were to split it into 6 pieces, 10 pieces, 100 pieces, we still wouldn't get the right answer. This is where integration comes into play. Let me explain. This is the basic idea of integration. I'll write up here, idea of integration. What we're going to do is we're going to take a limit. The limit as x approaches 0 of the summation from the index I equals 0. Remember, we start at the 0 second to 3 seconds of our velocity graph times the change in time, because of course, while we go over this interval, we're changing time from 0 seconds to 3 seconds and everything in between. And this is all equal to an integral of 0 to 3 of velocity with respect to time, this function, which in our case was t squared plus 1, dt. But what did I just write here, and what does it mean? We're going to go back to our red particle first. Our red particle was traveling with a velocity with respect to time of t squared plus 1. And you know what, I'll write that down here because that'll be easier to remember. Our little particle here was traveling at a velocity with respect to time of t squared plus 1. This summation series is summing up every single instance of this happening between I of 0 to 3. But what is this limit? What is all this garbage going on? Why did I rewrite our red particle from earlier? Let's say we were to split our velocity with respect to time into 6 pieces, twice as many as before. Our endpoints here are 0, 0.5, union 0.5 to 1, union 1 to 1.5, union 1.5 to 2, union 2 to 2.5 union 2.5 to 3. All I did was double the amount of intervals we had from last time. Last time it was 0 to 1, 1 to 2, and 2 to 3. We've doubled the amount of intervals that we had before. But instead of plugging these into just our velocity with respect to time graph, let's plug it into our little formula up here. Velocity with respect to time times the change in time. What might that equal? What we're going to do is we're going to take this formula in here specifically and use it with our velocity with respect to time graph. Now, I'm not going to write out every single number here because that's a lot of algebra and it's going to take a while. What we are going to do is we're going to mention that this is being multiplied by the change in time at a given point. So we're going to start from 0 to 0.5. The change in time in this interval is 0.5 seconds. But we're taking Vt of 0. So V of 0 times our delta t, which is 0.5, is equal to 0 squared plus 1 times 0.5. which is equal to 0.5, of course. 0 plus 1 is 1, 1 times 0.5 is 0.5. And we can do this for every single interval in here. This will help us not exclude any of the endpoints within our interval and make our estimation a lot more accurate, instead of excluding the time between 2 and 3 like we did before. Now, I'm not going to do the rest of the algebra here because there's quite a lot of it, so I'll save you the trouble. Over here, I'm going to write down all the left endpoints, and then I will write down what each one of these equals, so that way I can save you time. First, we have V of 0, times change in time, which of course was this interval here. V of 0 times 0.5 is 0.5. We did that one. V of 0.5 times the change in time is equal to 0.625. V of 1, remember these are all just the left endpoints, so 0, 0.5, 1, times the change in time is equal to, this one's just equal to 1. V of 1.5 times the change in time is equal to 1.125. V of 2 times the change in time is equal to 2.5. And V of 2.5 times the change in time is equal to 3.625. Now, if we were to add all of these together, all these different amounts of distance that our particle traveled, given our different time limits, we would get 9.375 feet. We're getting a little bit more precise here now that we're using a different formula instead of just straight plugging it into the velocity with respect to time formula, and we split it into more pieces. But this still isn't correct. And we know this isn't correct because if we were to plug in only the right end pieces, so 0.51, 1.52, 2.5, and 3, we would get 13.875, and that's not the same as 9.375. So in other words, we're still excluding something no matter what we do with only 6 pieces. So should we increase the number of these intervals to 10, 1,000, a billion? No, not exactly. But a more important question than that right now is what is actually happening when we split our velocity with respect to time graph into these intervals? What is happening when we split them in order to show how far a particle is moving between each section? Let's talk about it. So first, let's just draw the basic graph of t squared plus 1. This graph is labeled as t squared plus 1. It starts at 1, and this is 3. Remember, our particle is traveling from 0 to 3, so that's why I'm going to 3 here. Let's draw this dotted line as the boundary, and the function will look something like that. The shaded area under here is what the integral finds. We talked about that in the last integral video, which if you haven't watched, please go watch that first before I go any further into this video. Whenever we take an integral, it finds a function that'll find you the area under the curve. But how do we know that? Well, let's draw this graph, but with 6 pieces like we did before. Let's use blue, why not? We're gonna draw the same graph. It starts at 1 here, and it goes to 3. And this is the boundary, and this is our function. And let's try and describe this area underneath the curve with only 6 pieces. And in this case, we're going to be using rectangles. I'm going to use red to represent the rectangles. It's going to look something like this. As you can see here, we have formed 6 rectangles that give us a decent estimate of the area underneath this curve. Why are we making the rectangles? Well, that's a good question. Remember whenever we wrote down the summation series, in this case it was I equals 0 to 3, the function we had inside our summation was v of t, which is the function that represents this line, times delta t, which it looks very similar to length times width, doesn't it? And of course that will just form a rectangle. So that's why we're using rectangles here. But as you can see, these rectangles aren't very accurate, especially with only 6 pieces. You'll see there's a bunch overflowing at the top. It's a whole mess. It's not even close to exactly how much is under the curve. It's accounting for too much here. So how many rectangles do we need in order to figure out the exact area under the curve? Well, here's the problem. Rectangles don't curve. You may be able to tell by, the laws of a rectangle. So it'll take infinite rectangles to get the correct area underneath this curve. Let me write down one formula and then explain what's actually going on in the formula, and it'll make this make a lot more sense. Let me read this out to you. The theorem, let f be non-negative and continuous on A to B with a closed interval, so it includes the endpoints. The area under the curve on AB bounded by f of x, our function, the x-axis, this horizontal function here, and x equals a to x equals b is equal to the limit as delta x approaches 0 of the summation of k equals 1 to n of f times a plus k delta x times delta x. Now, I understand this is probably not blowing your mind right now, but that's because it's complex and hard to understand. So let's talk about it. Our delta x is in reference to the width of each one of these rectangles. Our f of a plus k delta x is the height of these rectangles. So whenever we take the limit of delta x, in other words, the width of these rectangles, as the width of these gets closer and closer to 0, we can sum that up in order to get the area underneath the curve bounded by the curve, the x-axis, and whatever numbers it's bounded by, in this case 0 to 3. So in other words, as delta x approaches 0, the width of these rectangles gets closer and closer to being 0, which gives us infinitely many more rectangles, which will give us the exact area under the curve. Now, obviously, I can't draw infinitely many rectangles, but that's the idea. And as you get more and more rectangles, they fill up the space more and more accurately until the width of the rectangles is basically 0, and therefore there are infinite rectangles between the bounded area. The area of all of those rectangles is the area under the curve. You see, rectangles are really easy to get the area of. It's just length times width. So we use them to understand the area bounded underneath the curve. And that is what's happening whenever we take an integral. I know that took a long time to get there, but that is what is actually happening when we take integrals of functions. This is known as the Riemann sum, and it's much easier to explain visually than it is to explain by just talking. We're going to do one example using this Riemann sum formula, and then we'll be done for this lesson. I know this is a lot of information to take in, but it's kind of an ingenious formula that blew my mind once I understood it, and I want to make it as easy and simple for you to understand, so let's do an example to help visualize what it looks like. Oh, and I want to mention that that area under the curve gives us the distance that that particle traveled. I'm not sure I mentioned that earlier, but that area underneath is the exact distance that that particle traveled. So whenever our speed or velocity is changing, and we have a formula to represent that rate of change, we can use an integral and then find the area under the curve to figure out how far said particle or object went. I'm not sure I said that earlier, so I want to make that clear. Now let's do the example problem. In our example, we want to find the area under the curve f of x is equal to x cubed bounded by 0 to 1. So that'll look something like this. Let's use the green marker, why not? Here's our graph, and here's 1, and here's 0. And x cubed will look something like this. It'll come down, and then we shoot way up. So it'll be this tiny area here between 0 and 1. So we're looking for that area. How can we solve it? Well, we just had a formula earlier that can tell us exactly what that area is under the curve using infinite number of rectangles. So let's do it now to figure out what this area is. A couple things to note. I didn't mention what delta x equaled earlier, so we're going to write it down up here. Delta x is equal to b minus a divided by n. So in our case, our delta x is equal to 1 minus 0 divided by n. So delta x is equal to 1 divided by n. We'll use that in the formula. And then the other thing we need to figure out before plugging it into our Riemann sum formula is that other part, f of a plus k delta x. What does that equal? Well, we know what delta x equals, we know what a equals, let's plug that in. So f of a plus k delta x is equal to f of 0, a is 0, right here, this is our a value by the way, a and b, f of 0 plus k times 1 over n, this was our delta x from up here, and this is equal to f of k over n. Now 0 obviously doesn't change anything in here. Multiplying the k to the top, we get k divided by n. So now we can plug in this along with knowing what delta x is into our Riemann sum formula to figure out the area underneath this curve. So what I'm going to do is I'm going to write the formula over here again because I don't think I've rewritten it. The limit as delta x approaches 0 of the summation of k equals 1 to n of f of a plus k delta x times delta x. And this will give us the area under the curve. Let's plug in our values here in order to solve this problem. Moving down here, we get area, represented by capital A, is equal to the limit as delta x approaches 0 of the summation of k equals 1 to n of f of k divided by n times 1 divided by n. What we're going to do now may seem a little weird. We need a lot of rectangles. So in order to go to a gigantic amount of rectangles, we need this limit to approach something gigantic. What we're going to do is we're going to change this formula into a is equal to the limit as n approaches infinity, and then inside is mostly the same. We get k equals 1 to n of f of k divided by n times 1 divided by n. We need a gigantic amount of rectangles to get the correct area, so we just need this n value up here to approach something gigantic. Oh, and to clarify why we changed this delta x that approaches 0 into n equals infinity, well, we know delta x is equal to 1 over n from earlier. So in order for 1 over n to approach 0, n has to equal infinity. I apologize, I should have mentioned that earlier, but that's why we replaced this with n equals infinity. They're equivalent, we didn't change the equation, I just forgot to actually give my reasoning why. That's my mistake, but I hope that clears it up for you. So we know that our f of x is equal to x cubed, so we need to plug in k over n to x cubed, which just is k over n cubed. Let's write that down over here. We get the limit as n approaches infinity of the summation k equals 1 to n of f of k of n is just k divided by n cubed times 1 over n. Next, we need to multiply these two functions together. Cubing a fraction just cubes the top and cubes the bottom. So this is k cubed divided by n cubed, and then multiplied by 1 over n is k cubed times 1, which is 1, and then n cubed times n is n to the 4th. So let's write that down over here. The limit as n approaches infinity of the summation k equals 1 to n of k cubed over n to the 4th. We're getting a little bit more simple. This looks like something we could solve potentially. What we're going to do here is we're going to take this n out. We can just yoink that out of our summation and pull it to the front. You may remember when we did derivatives, or even in the last lesson where we talked about some integral solving strategies, we can take out constants. We're going to take this n out to the front and change this to the limit as n approaches infinity of 1 divided by n to the 4th times the summation k equals 1 to infinity of k cubed. If we were to multiply this back in, we would get k cubed divided by n to the 4th. Now we finally have our k isolated and can figure out what this summation equals. Although this shouldn't be an infinity, that should be an n. But the biggest thing that happened here is one of our summation formulas from earlier popped up. We talked about I cubed, and instead of I, we have k in both of these places. So we're going to rewrite this problem by substituting this summation for its simpler algebraic version. This will now turn into the limit as n approaches infinity of 1 divided by n to the 4th times n squared times n plus 1 squared, all divided by 4. Remember earlier, the summation of I cubed, or in this case k cubed, is equal to this algebraic expression. Now we're going to simplify this down a little bit. We can cancel out this n squared and take out 2 of our powers in n to the 4th, and then we'll rewrite that down here. This now all turns into the limit as n approaches infinity of n plus 1 squared, and then multiplying our bottom, we get 4n squared. Now it may not be obvious, but this is a 1/4 constant, which if you remember, we can take to the front of limits to make this a little bit simpler. So this now turns into 1/4 times the limit as n approaches infinity of n plus 1 squared, all divided by n squared. Now we need to expand this n plus 1 squared. Expanding n plus 1 squared is equal to n plus 1 times n plus 1, which is equal to n squared plus 2n plus 1, all divided by n squared, which then we can split by addition. Since our numerator is split by addition, we can split each of these individual values to be divided by n squared, which is then equal to n squared divided by n squared plus 2n divided by n squared plus 1 divided by n squared. This, of course, is just equal to 1, so we get 1 plus 2n divided by n squared. Can't really simplify that at all. 1 divided by n squared, also can't simplify that at all. 2n divided by n squared plus 1 divided by n squared. Now we can finally plug in this limit of n equals infinity. Plugging in n equals infinity to just the number 1 is just 1. So I should probably clarify this is coming down here, just 1. And then if you remember, our tower of power has n squared as a higher power than 2n. Our n squared will grow at a more rapid rate than 2n, so whenever you make them both infinity, this gigantic infinity will divide this smaller infinity to be 0. And that's the same case here. If we were to plug in an infinity, divide a constant by infinity, that's basically 0. So this is 1 plus 0 plus 0, all multiplied by our 1/4 that we had outside the limit. So our answer is 1/4. That's the area under our curve of f of x is equal to x cubed bounded by 0 and 1. I know that was a lot of work, but trust me, integrals are not nearly this difficult. We will not be using the Riemann sum over and over again, but this Riemann sum shows you how integrals work and what they are. I hope you guys found this video helpful and you learned something, and if you liked it and thought that I taught you well, or you just liked the video and you want to see more math lessons, consider subscribing to this channel. If you want to learn more of Calculus 1, check out the playlist that I have linked here, and once again, consider subscribing. I'll see you all in the next video.